Today we are going to continue our discussion of imaginary numbers or numbers. And yesterday we learned how to add, subtract, and multiply them. Today we are going to talk about dividing with complex numbers, as well as how it looks when we're solving equations that have solutions, though. 3 learning goals for today. The first is to be able to solve quadratic equations with complex solutions by taking square roots. So we already did a previous lesson on just the solving by square roots. So now we're going to be doing all those exact same steps, except some of our answers are going to have i's in them. So example 1, solve the equation. So x squared minus 16 equals 5x squared. Well, if we want to solve by taking square roots, we need the squared term alone. So since I have 2 different squared terms, I need to combine them. So first I'm going to subtract x squared on both sides to get those terms together. So then I've got negative 16 equals 4x squared. Squared term is still not alone. I need to divide by 4. So I'm going to switch the sides here. I've got x squared alone, and on the other side, negative 16 divided by 4 is negative 4. Once the squared term is alone, then I can take the square root of both sides. So square root here, square root here. On the left, square root of x squared is just x. On the right, square root of negative 4. We know that the square root of 4 is 2, and because of the negative, we make it I. And then, because we were solving an equation, do not forget that you need a plus or minus. So plus or minus 2i is going to be your answer there. Let's look at one more of those. Again, it's all the same steps as what we did in, I think it was 5.3b. But we need to get the squared term alone here. This 4 is in my way, so I'm going to divide. So that gives me x minus 2 squared equals negative 1/4. So now that the squared term is alone, I'm going to take the square root on both sides. So on the left, I've got x minus 2. On the right, I've got a plus or minus, and then the square root of 1/4. If I write my work up here, remember that we give them each their own symbol. Square root of 1 is 1, square root of 4 is 2, and then because it was negative, that means I need my I. I'm not done here yet. I'm done with the imaginary part, but x still isn't alone. I've got this minus 2 over here, so I need to add 2 to both sides. Again, we treat those i's just like we do other variables. These are not like terms. I can't combine 2 with a 1/2 x, so that means I also can't combine a 2 with a 1/2 I. So that's just going to stay 2 plus or minus 1/2 I as your answer. All right, so that takes care of our first learning goal. Second learning goal is to find a complex conjugate. So we've got a little bit of background information on that. You cannot leave an I in the denominator because I stands for the square root of negative 1. So leaving an I in the denominator is the same thing as leaving a radical in the denominator. So just like we had to rationalize when we had radicals in the denominator, we have to rationalize denominators that have i's. So in order to do that, we're going to multiply by something we call the complex conjugate. The complex conjugate, even though it says complex, is really very simple. All you're going to do is take the exact same complex number, but make the sign opposite for the imaginary part. So here's a quick example. If 2 plus 3i is the complex number, I take the same complex number and I just change the sign. So 2 minus 3i would be the complex conjugate of 2 plus 3i. So just real quickly here, just to identify complex conjugates, this first one, again, I keep everything the same except that I change the sign. So that would be 3 plus 4i. So you quickly in your head tell me what you would get for B's complex conjugate. Hopefully you said 5 minus 2i. C, there is no number in front. That's okay. I just need to change the sign on the imaginary part, so it's going to be positive I. Last one, you do it. What would the complex conjugate of 1 plus I be? The answer should be 1 minus I. So that's our second learning goal. Hopefully now we can find a complex conjugate. Last goal is to be able to rationalize denominators so that we can simplify those complex expressions. So now that we know how to find a complex conjugate, we need to use that. So they help us to rationalize the denominators. So we're going to multiply the numerator and denominator by the complex conjugate. So remember, it's just the complex conjugate of the denominator. I don't care if there are i's in my numerator or not. I just can't have i's in my denominator. So when I look at my denominator here, the complex conjugate is exactly what I did in A there. It's going to be 3 plus 4i. Whatever I multiply by on the bottom, I have to do the same on the top. So that's also 3 plus 4i. Now, when I go to multiply these now, this brings in what we did in the last lesson. I have to FOIL these because these are binomials times binomials. So on the top, FOIL, firsts, would give me 9. Outsides, 3 times 4i gives me 12i. Insides also gives me 12i. And my lasts, 4i times 4i, is 16i squared. So my pen got stuck there a little. There we go. On the bottom, that's a sum and difference pattern. It's going to be very similar to what I had in the numerator. 3 times 3 is still 9. On the outsides, 3 times 4i, I've still got plus 12i. But on the insides, it's a negative 4i, which makes this a negative 12i. And then my lasts, negative 4i times 4i is negative 16i squared. So now I'm going to simplify the numerator, simplify the denominator. In the numerator, these are like terms. This 16i squared is really just a negative 16, which then is a like term with this 9. So 9 take away 16 is negative 7. 12i plus 12i is 24i. On the bottom, very similar, this negative 16i squared really becomes a positive 16, which is a like term with that. So 9 plus 16 is 25. My I terms in this case cancel each other out because they're opposites. So now I look, I have no i's in my denominator, there's nothing that I can reduce, so this is simplest form. All right, I'm going to try that again. Complex conjugate of the bottom, you see it up here, is 5 minus 2i. So I need to multiply by 5 minus 2i on the top as well as on the bottom. So on the top, firsts, 5 times 2 is 10. Outsides, 2 times negative 2i is negative 4i. Then insides, 5 times I is 5i. And lasts would be I times negative 2i, so negative 2i squared. On the bottom, also a sum and difference pattern. That's the whole point of the complex conjugate, to get the i's to drop out, so they should be a sum and difference. It should cancel out. So firsts, 5 times 5 is 25. Insides are negative 10, or outsides are negative 10i, insides are positive 10i. Again, if you know that those cancel out, that's fine if you don't want to write them. And the lasts then would be negative 4i squared. So now I need to simplify. So these are like terms because that negative 2i squared is really the same as a plus 2. So 10 plus 2 gives me 12. These are like terms. Negative 4i plus 5i is positive 1i. On the bottom, again, on a sum and difference pattern, these drop out. Negative 4i squared is really the same as a plus 4. So 25 plus 4 is 29. I look, I've got no i's in the denominator. There's nothing that can be reduced, so that means that is my final answer. All right, I'm going to walk you through just one more here. Complex conjugate on the bottom is 1 plus 3i. So I'm going to multiply by that on top and bottom. On the top, when I FOIL it, 1 times 1 is 1. Outsides, 1 times 3i is 3i. Insides, 2i times 1 is 2i. This didn't come out very well. That is a plus sign. And then lasts, 2i times 3i is 6i squared. On the bottom, again, sum and difference pattern, so you should start to notice the inners and outers drop out. So firsts, 1 times 1 is 1. Lasts, negative 3i times 3i is negative 9i squared. Again, you don't really need to write those middle terms. If you're afraid you're going to mess it up, then go ahead. But you don't need to because they will always drop out with the complex conjugate. This plus 6i squared is really the same as a minus 6, so that becomes a like term with the 1. So that gives me negative 5. These are like terms. That's 5i. So negative 5 plus 5i. On the bottom, the negative 9i squared becomes a plus 9, so 1 plus 9 is 10. I have no i's in my denominator, so that's great. This one, when I look and see, this does reduce. I can put that in a simpler form because all three terms, it has to be all of them, all of those terms there are divisible by 5. So I'm going to reduce that by 5 and make it negative 1 plus I over 2. So if it reduces, you will need to do that. All right, I've got 2 to try on your own. And so pause it and work these out quickly and then come back to see if you've gotten them right. All right, so on D, I'm going to be multiplying by 3 minus 2i on top and bottom because that's the complex conjugate. On the top, that gives me 12 minus 8i plus 6i minus 4i squared. Then on the bottom, I get 9. The inners and outers are going to cancel, and so then I've got minus 4i squared. So like terms, this becomes a plus 4. So my plus 4 and my 12 give me a 16. Negative 8i plus 6i is negative 2i. And then on the bottom, negative 4i squared again becomes a plus 4. So 9 plus 4 is 13. I look, i's, there aren't any in the denominator. There's nothing to reduce because there's no common factors between all three terms. So that is it for that one. Last one. If you haven't already tried it, again, pause and do it yourself first, and then come back to see if you have it right. So complex conjugate here is 7 minus I. So I multiply by that on the top and the bottom. So on the top, it's going to give me 49 for my firsts. Outsides are negative 7i. Insides are also negative 7i. And my lasts are positive I squared. On the bottom, sum and difference, so that means the inners and outers will drop. Firsts are 49, lasts are negative I squared. On the top, I squared is negative 1, so I take that negative 1 and combine it with the 49, so that gives me 48. These, negative 7i minus 7i is negative 14i. And then on the bottom, minus I squared becomes a plus 1, so 49 plus 1 is 50. My i's are gone from the denominator, so I'm good on that. Looking for ability to reduce. All of these are even numbers, which means at the very least they're all divisible by 2. So if I reduce them all by 2, that gives me 24 minus 7i over 25. And there's nothing else that divides all three that have to be divisible by all three to reduce. So that is all I can do. And that's it for today.